Alright, so here's a video for these notes that we're about to do, 210 to 212. I had made a video in class, but then it got deleted, and so anyway, so I'm going to go kind of quick. I'm just being pointing to stuff, so you might need to pause and to write stuff down. I'm just going to talk through it. So, your general form for a log function is going to be this right here, where b is greater than 0 and b is not equal to 1. You don't want a base of 1 because 1 to any power would be 1 again. And this a is not equal to 1. That's not necessarily true there. All right, and so you know that you have logs and exponential functions are inverses of each other. So then remember that when you used to have a exponential function. So, go ahead and read through this right here, but an exponential function, you got equal length intervals right here, and you're multiplying by 2. So that's where you notice that there's a proportional output. Okay. Over here, since logs and exponential functions are inverses of each other, now that idea is going to be swapped. Right? So now your equal length interval will be on your output, and you'll have your input is going to be where you see a proportional rise. Okay, like multiplying by 2. All right, so down here we're just deciding on this example here. So this guy, I see my equal length interval, I see my multiplying by 1/2, so that's exponential. I see here I'm multiplying by 3, and over on the right side is I have my equal length intervals, and so that's a log function. Letter C is neither. This is proportional, that's proportional, multiplied by 10, multiplied by 2, so that's neither one. And over here, my equal length interval is on the right, that's decreasing by 3, and then I'm multiplying by 2 here, so that's a log function. Right? So when you do logs and exponential functions, they are inverses of each other, so you should be able to plug them into each other and you get x back out. So we got an example down here. So f of x is here. I'm going to be plugging this up there. So whenever you have a base matching bases, like you have a log with the same base as your base down here, they effectively cancel each other out and you get an x there. So now I'm going to be taking this problem and plugging 3 to the x there. So same idea. You have a log with the same base and you have an exponential function with the same base. So these cancel each other out and you get x. Also, there's that rule that when you have an exponent, it can be brought to the front. So you have x times log base 3 of 3. And 3 to the power 1 is 3. So this is just really x times 1 equals x. All right, one other little part here. All right, so we got an exponential function, some random exponential function that has these points on it. Find the average rate of change of the log function for that base. So, we have to turn the points around, switch the x and the y, and then do our average rate of change. So 3 to the 27 is now our x values, and we go ahead and subtract the y's, subtract the x's, and reduce. Okay. So right now, on your homework paper, you should do the front page. You should do these 4. You should do this middle part, and I messed up the numbering here, but you should also do these 2 right here, these 2 parts. Okay. All right. Then I'm going to move on to the next piece. So in class, we did these notes, and then we did a little bit of homework. Then came back for some notes, then did a little bit of homework. So this next part is about characteristics of graphs of the functions. So remember, this is just like your generic log function, probably going through 1, 0 right here. And, b is greater than 0 always. And a is greater than 0 here. So this just means that this is like a regular problem. A is less than 0 is the same problem here as same function, but when a is less than 0, that means that this number is negative. So this has been reflected over the x-axis. So you see it's flipped upside down. Okay. Our domain is from 0 to infinity. You can't do the log of a negative, and you can't do the log of 0. All right, so that's why we're held back. Nothing is over here on the left-hand side. So our domain is from here over, anything past 0. All right, and the range is always negative infinity to infinity. So just up forever, down forever, up forever, down forever. So it's important that you realize you're not going back behind 0. So when we go and do some of our end behavior later, you're going to see this notation. X is going to 0 from the right, because you can't approach 0 from both sides because there's nothing over here. So you're only approaching 0 from the left, and that's going down to negative infinity. And when you're going on the right side, x is going to infinity, and you're going up forever. Okay. Whereas if you have a log function, with a negative in front, it's basically this graph, but it's like reflected over the x-axis, so it looks like that. So when you're approaching 0 from the right, this is going up. When you're approaching infinity, your graph is going down. Okay, so the other things you have to identify are whether you're increasing and decreasing. All right, so look, your graph is, your y values are getting higher, so you're increasing. Y values are getting lower, you're decreasing. Concave up, so it's concave down, concave up. It's always one or the other. And so that should be pretty easy for us. All right, so this last little bit right here, this graph is concave up, and the y values are getting smaller, so it's decreasing. Y value is getting larger here. I had to draw my own picture, and I am increasing. Concave down. Remember, you're concave down because your slope is positive, less positive, less positive, less positive. So your slopes are decreasing. All right. So remember, the one thing about a log, you cannot take the log of a negative or 0, right? So this number has to be greater than or equal to 0. So x is greater than or equal to 0, that's your domain. And then the range is always negative infinity to infinity. The graphs go up and down forever, all the time. So it's the same range all along. So that means that what I need to worry about is this part right here. X minus 3 has to stay greater than 0. So that turns into x has to be greater than 3. So there's my domain. Here, 2x plus 3 has to be greater than 0. So that turns into x is greater than negative 3/2. And there I go. All right, so now on this paper here, you can do the whole front page and the whole second page right here. Okay, that's your job to do that. And let's see. So do that and come back. So here we go with the last little part. So you learned all of this in Algebra 2 Honors last year, how to basically condense and expand logs. Okay. So remember that multiplication splits up into addition. So when you see like log base 2 of 5x, you can expand that into log base 2 of 5 plus log base 2 of x. Now usually we don't expand things. We usually like put them back together, like take this and go there, but you need to know both. All right, division turns into subtraction, and a power. Power out here goes to the front and multiplies to the front. So these all have like their kind of like rules coming from exponential functions, right? Like if you have 2 to the x times 2 to the y, remember that turns into 2 to the x plus y. So multiplication is tied to addition. And if you had 2 to the x over 2 to the y, remember that turns into 2 to the x minus y. So division is subtraction, they go together. And when you have like 2 to the x and then you have a y here, so that would mean 2 to the x times y. So powers turn into multiplication. So this is like the exponential rule that we follow to basically get the log rule. So every exponent rule has also a log rule that goes with it. All right, they're tied together. So if we want to expand this, there's 2 parts. So log of 10 plus, because it's multiplication, log of x squared. That 2 can come out front. All right, and log of 10, I know the answer to that. 10 to the 1 is 10, so we can put a 1 there. Right here, I got 1, 2, 3, 4 parts, so we can expand them. Both of these down here, they're both on the bottom. They're both divided. That's why they both have a minus. And then furthermore, log base 3 of 9, 3 squared is 9, so the answer to that is 2. I can simplify. All right, over here. I have this going on here, so let me write a little step in between. So that 2 is going to come up, so I got log of x minus 1 squared, that plus log of 4. And this guy, you notice how these have the same, they're the same, right? They're like common terms. 3 log of x's and 2 log of x's, so that's minus 5 log of x's. So that's x to the 5th, right? That 5 goes up there. So these 2 are multiplied, divided by x to the 5th. Now, in this one right here, this 3 is sitting there, so it's not tied together with the x. There's no parentheses, so that 3 is by itself. So I have to turn this into a base 4. So 4 to the 3rd power is 64. Like the answer to this is 3. If I saw this expression, I could put a 3 in its place. So I turned that 3 into an expression with base 4. log base 4. So 4 to the third is 64, so this is it. So basically have this minus that. So subtraction turns into division, so 64 is on the bottom, and x to the fifth is on the top. All right, and we are going to do these notes up until right here, up until example 3 will stop. So this is just some condensing. Addition turns to multiplication, subtraction, division. Both of these are subtracted, so they're both underneath. They're both divided into the x. Right here, x to the third comes up and then divided by y. All right, 2 comes up, 5 goes up, and 4 just stays. Now notice the 5 is, this part is negative, so that's why that b to the fifth is on the bottom. The other 2 are multiplied on the top. I have to turn 2 into something with log base 6, so I did it for 36. 6 to the second is 36. The answer to this is 2. So this plus that, I have multiplication because that's addition. Here, I have division, so it's going to turn into subtraction. So I don't have enough for this. There's not 3 parts right here. There's just the x and the y, so d is no good. All right, you might want to decide between these two, but you have to think to yourself, 2 is only for this x, it's not for the y. If the 2 were out here, then I would say this problem, because the 2 is in front of both of them. But here, 2 is just for the x, so we're going with letter C, and the y is on the bottom. All right, and the rest of it we'll do next time. So your job is to have all of this done up through number 24. So stop right here. And that is it. Bye-bye.